Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to inductance and inductive circuits related to power systems engineering, the transmission line parameters. So in this video we are going to discuss about the AC analysis of inductive circuits. Okay, so the first thing that we have to discuss is the concept of inductive reactance. In the capacitive AC analysis we discussed about capacitive reactance. Inductive reactance is same as that, but here it is provided by the inductor. Okay, so it is the opposition to current flow in the circuit which is provided by the inductor or coil. So the inductive reactance XL, because of an inductor of inductance L, is given by XL is equal to omega L, where omega is the angular frequency in radians per second and L is the inductance in Henry. XL has the same unit as resistance because it is opposition to current flow, which is ohm. This is the simple expression. In terms of complex numbers or the complex representation, it is expressed as j omega L plus j omega L. Capacitive reactance was expressed as 1 by j omega C or minus j by omega C. Here it is plus j omega L. J is in the numerator. Okay, now let us say we first take a purely inductive circuit. We have an alternating voltage connected to a pure inductor of inductance L Henry. This produces alternating time varying current. Now here this alternating EMF or voltage is expressed as Et is equal to E0 sine omega t. Now we know from Faraday's law, Lenz's law, the concept of electromagnetic induction, that when current through a conductor or the coil it changes, we are dealing with a time varying EMF, alternating EMF. So obviously there will be alternating current. So whenever current will change, there will be a change in flux. Change in flux produces EMF. So obviously there will be EMF generated here. Okay, a time varying EMF here, which will be equal in magnitude but opposite in phase, opposite as per Lenz's law to the applied voltage. This is the induced voltage across the inductor. It will be equal in magnitude but opposite in phase. Okay, so here this will be like this, where VL is equal to L minus L di by dt as per Faraday's law, Lenz's law, the concept of electromagnetic induction, because we know that minus N d phi by dt is equal to minus L di by dt, where I is the current flowing through the inductor. Okay, so when we simplify this, it becomes E0 sine omega t is equal to L di by dt. We take di on one side, so it becomes E0 by L sine omega t dt. On integrating both sides, we get I is equal to minus E0 by omega L cos omega t, which is equal to E0 by omega L sine omega t minus pi by 2. So here E0 by omega L, that is equal to the amplitude of the alternating current. So this becomes I0 sine omega t minus pi by 2. So here if you pay attention, this is the expression of the alternating current flowing in the circuit, and this E0 sine omega t, that is the expression of the applied alternating voltage or EMF. So if you see here, the current lags behind the voltage or the EMF by 90 degree minus pi by 90 degree or pi by 2 radians. It is lagging behind, whereas in case of purely capacitive circuits, the current used to lead the applied voltage by 90 degree or pi by 2 radian. It was plus pi by 2. Okay, so in purely inductive circuits, the current, the circuit current lags behind the applied voltage ET, because ET is equal to VLT. Okay, ET is equal to VLT. Okay, in terms of magnitude, I'm talking about the magnitude. It is equal in magnitude. So this here, the current, it is lagging behind the voltage by minus pi by 2 or pi by 2 radian or 90 degree. Okay, so this is the simple thing. In purely inductive circuits, the current lags behind the voltage by minus pi by 2, or you can say that the voltage leads the current by pi by 2 radian or 90 degree. Okay, so here it is the voltage across the inductor or the applied EMF, the RMS value or the virtual value we are talking about. So here voltage leads by 90 degree or pi by 2 radian, or current lags behind the voltage by 90 degree or pi by 2 radian. And this is the phasor representation. In terms of waveform representation, this is the blue one represents the alternating EMF or voltage, whereas the red one represents the alternating current. Okay, so the phase difference is pi by 2 radian, current lagging behind the voltage. Okay, now the average power for such a circuit is 0, and the instantaneous power at any given time is the product of the time varying EMF and the time varying current. That gives us, using trigonometric identities, simplifying it, we get minus E0 I0 by 2 sine 2 omega t. So this is the analysis of a purely inductive circuit. Next is when we have a resistor connected to a pure inductor, RL circuit where R and L, resistor and inductor, are in series. So here a concept comes which is similar to what we faced in the RC circuit, impedance, net impedance of the circuit. So in terms of complex analysis, it becomes the net impedance is equal to R plus j omega L, because we discussed the inductive reactance of a pure inductor is expressed as this. So R plus jXL or R plus j omega L, that is the net impedance or the net opposition to the current flow. Unit is ohm, and unit of impedance is ohm. In case of capacitance, it was R minus j by omega C or R minus jXC. Here it is R plus jXL. Okay, so this is the net impedance. So now here, for a purely resistive circuit, both the voltage and current, they are in phase. There is zero phase difference between them. Okay, this is for purely resistive circuit. No phase difference. No phase difference or zero phase difference. Now, for a purely inductive circuit, the current lags behind the voltage by pi by 2 radian or 90 degree. Okay, the phase difference is 90 degree or pi by 2 radian. Okay, so for a RL circuit, it will be somewhere in between 0 degree to 90 degree or 0 radian to pi by 2 radian, somewhere in between that. So yes, for a RL circuit, the phase difference will be phi, which is in between 0 radian and pi by 2 radian, or 0 degree and 90 degree. So this is the phasor representation, where we have taken the current, the virtual value, the current, circuit current, as the reference phasor IV, the inductor voltage, which is equal in phase and opposite in magnitude to the applied EMF, that is leading the current by 90 degree. The voltage drop across the resistor, it is in phase with the circuit voltage. Okay, it is in phase with the circuit voltage. So the net EMF, which is the virtual value or the applied EMF, that is the resultant of the voltage drop across the resistor, which is in phase with the current, and the voltage drop across the inductor, which is leading the current by 90 degree. So we get a net phase difference of phi, which is in between 0 degree, okay, which is in between 0 degree and 90 degree. Okay, we get somewhere in between phi. Okay, so here the net EMF, okay, that is the resultant of these two phasor, representations. So it is VR square plus VL square. Okay, voltage drop across the resistor, voltage drop across the inductor. Now if you want to calculate the phase angle, you can use any trigonometric ratio, sine, cos, tan. Here I am using tan, which is VL by VR. Phi is equal to tan inverse of VL by VR. Voltage drop across the inductor, voltage drop across the resistor. Now if we divide the current in all of this, VR by IV, VL by IV, EV by IB, if we divide all that, this is called as the voltage triangle. Okay, similar to what we have discussed in the capacitive circuit, this is the voltage triangle, where we have only the voltage phasors with respect to current. If we divide each of these phasors by current, we will get the impedance triangle, where EV by IV is equal to Z, VL by IV is equal to XL or inductive reactance, and VR by IV, that is equal to R. Okay, so this is the impedance triangle. Okay, here by mistake I have included this. No, just disregard this current thing. Okay, only this triangle XL R Z. Okay, only that much is there. Okay, disregard this. So no, it will only create confusion. Just by mistake it got included in this diagram. Just okay, exclude this. Only Z R XL. So here again the net impedance is equal to magnitude of the impedance, where we have expressed R plus J omega L, which is R plus J XL. So the net impedance is equal to R square plus XL square, which is R square plus omega L whole square. Impedance can also be calculated as EV by IV, and tan phi can also be, the phase angle can be calculated as XL by R, or phi is equal to tan inverse of XL by R. Okay, so this is the phasor representation, and this is the waveform representation. Again the same thing, the current is lagging behind the voltage, but here the angle is somewhere in between 0 radian and pi by 2 radian. Okay, phi radian. Okay, but there is a lagging thing, the current is lagging, but not by pi by 2 radian or 90 degree, but lesser than that, phi radian. So this is the AC analysis of inductive circuits. Okay.